All right, so let's start. So first, an important announcement, because the webcast from Thursday was delayed. We are removing greedy algorithms from Thursday's midterm. Don't worry, they will be included in the next one. So today's material is not really necessary for Thursday, but it will be pretty much a core topic in the next midterm. Okay. So today we're going to cover a very beautiful greedy algorithm. It's called Kruskal's algorithm. It solves a problem we're about to define. It has to do with minimum spanning trees. Okay, and kind of the greedy strategy will be maybe clear at the beginning, but proving why it works is actually a journey into understanding the structure of minimum spanning trees, and then we'll study something known as the cut property. And this will be like a very sort of non-trivial explanation for why the greedy strategy works. Okay, so it's going to be planned for today, learning about one greedy algorithm. Okay, so let's define the problem that we're studying. It's called minimum spanning trees. Usually abbreviated MSTs. Okay, and the input is a graph with weights. Now, notice that all of today is going to be with an undirected graph. Okay. And the weights but sometimes we call them lengths, sometimes we call them weights. Doesn't really matter. This is just some English word. There is some edge labels. Okay, and actually, it will not matter a whole lot whether the edge weights are positive or negative. I'll explain why in a moment. And what you want to find is a kind of an MST. Okay, what is an MST? So it is a tree T. Okay, in G that minimizes its weight. So let's define weight of T to be the sum over all edges in the edge set of T, weight of E. Okay, but so far I haven't put any interesting condition. If you just want to minimize the weight of a tree, you just output an empty tree. But it has to be a spanning tree. Okay, spanning means that this tree touches all vertices of the graph. Okay, a tree in G that minimizes this one and touches all vertices in G. Okay, so that is the problem. Let me just work through an example first so we understand it, and then we'll make sure we understand the abstract formulation, okay? So, as an example, let's write down an undirected graph. Notice I'm not putting the arrows on the edges because it is undirected. Okay, but I do have to put weights because we need them. So here's 1, 5, 3, 3, 1, 5, 6, 4, 5, 2. Okay, so this is an instance of our problem. The graph plus the weights, and we need to find the minimum spanning tree. Okay, we need to find a subset of the edges, okay, that touches all the vertices and it has minimum weight. Okay, so okay, it's a small example. We can try to kind of eyeball it. Maybe this one here looks pretty attractive, right? Has small weight, connects two things that we haven't seen yet. So we could say, you know what, I'll just throw it in the bag. Maybe I hope I want to get stuck later. So now I have C and E covered. Okay. So if I did make this choice, maybe I'm looking down here and say, look, I'm going to have to get to F somehow. I could go through 6 and 5. 5 looks better to me. So maybe let's go for that, right? All right, so from C, so I need to somehow get to B. It seems like going from A to B is going to be a pain. So yeah, I can go either from C to B or E to B. It's going to cost me the same, right? Maybe I can pick this one. All right, so I got B covered. I need to somehow get to A, right? But now I have like a bit of a trade-off, right? I can either pay for 7 here or 6, right? Because I'm going to have to somehow cover both A and D, right? So I could either go this way. This is not a path. It's just like I need to go. In the end, I'm going to have to sum all the edges that I pick. So either I'm going to pick these 2 edges or these 2 edges. So this is 7. This is 6. Looks better. Okay? Now what we have is that we have a tree. Okay? So there are no cycles and a certain number of edges. We'll talk about trees abstractly in a moment, but this is a tree. And I've covered all the edges, and let's see what is the weight of this tree. So we have 1, right? Plus 2, plus 3, plus 4, plus 5, right? That's 15, right? So in this case, we just eyeballed it, right? This is an MST. We kind of went tried to kind of propagate constraints. But yet it's still not clear what should be like a generic algorithm, okay? But at least as far as the example is concerned, is the abstract problem formulation clear? We're given a directed graph, we have weights, and we're going to look for an MST. Is it clear? So that's the problem we want to solve today. Okay? So I want to make some remarks, just because we've spent so many lectures on shortest paths, and I want to say that this is a problem that is different from shortest paths. Notice that, first, there is no distinguished start vertex. There is no special vertex here. Okay? There is no S. Okay? There's just a tree. Okay? So just say MST is different from shortest paths. Remember that, just don't get confused. One way that this comes up really concretely is that I claim that we can assume for this problem, without loss of generality, that all the weights are non-negative. This is unlike what we do for shortest paths. This is one way to kind of really see that they behave as problems very differently. Can anybody explain why I can assume without loss of generality that the weights are non-negative? Yeah?
You could add some positive amount to each weight, and that would eventually make the MST, because all MSTs have the same number of edges.
Great. So thank you. So the suggestion was that we can just add the same large enough quantity to all edges. And the reason why it doesn't change the answer is because all MSTs, we'll see, have the same number of edges. How many? N minus 1, V minus 1. Okay? So all of them will go up by the same amount because all edges will get increased by the shift. Notice that in shortest paths, you weren't guaranteed that all shortest paths have the same length, right? So this is one reason in which a sort of a reasonable looking but incorrect statement that you can just assume without generality that lengths are non-negative in shortened paths doesn't work is because paths have different lengths. But here, because we're focusing our attention on trees, they all have the same number of edges, so it's okay to bump it up. Okay? Separately, we actually don't care a whole lot about whether the weights are positive or negative. It's just I wanted to kind of understand this difference. Okay? So here another point. So there are 2 points to this. One is that there is no special vertex. Another way in which you can see that they're different is that you can say WOG in MST, the weights are non-negative because kind of all trees have v-1 edges. Okay? This is just to kind of, as a remark, that may help you like understand the problem a little bit better. Okay? So because we're going to discuss trees, we're going to go on a brief detour to talk about what are trees abstractly as graphs, right? So you may be familiar with trees as this kind of, there's a distinguished root, and there are like children dangling off with their own children, and so on and so forth. In the trees that we'll consider today, there's no special root. I mean, you can find one, and you can designate in a tree a particular node special and call it a root if you want. But we want to understand them more abstractly, kind of rootless trees. Okay? So in particular, in the definition, what is a tree? And the definition of a tree is a connected acyclic graph. Okay? So it's almost a DAG, except it's one piece. Okay? So, and now we have a definition. We're going to prove some simple claims about them, so we just get comfortable with trees. Okay? Because to solve this problem, we're going to design an algorithm that's going to rely on some of these properties. Okay? So, first claim we're going to prove is that if G is connected, then we have an equivalence between two conditions. Condition A, that G is acyclic. And condition B is that the edge set of G is exactly n-1. So the graph has n-1 vertices. Okay? So let's just play with these conditions and make sure we understand them. Okay? Notice, by the way, that one direction of these conditions we have already used, and I didn't really justify it. I said a tree has v-1 edges. What is a tree? A tree is a connected acyclic graph. So if you look one direction of this condition, I'm saying if you have a connected acyclic graph, that is a tree, it has v-1 edges. Okay? We just used it here. Okay? It feels intuitive, but we should kind of prove it. So let's first see the condition that A implies B. Okay? Another way to say it is that if G is a tree, then its edge set is exactly v-1. Okay? All right. Well, certainly, we do not expect the number of edges to be less than v-1 for a simple reason. If we have less than v-1 edges, what is going to happen? There's going to be a lonely vertex, right? So it's not going to be connected. Okay? So, but why not more than v-1? So one way to view it is to say, you can say start from an empty graph and we're going to add the edges one by one and see what happens. Okay? Okay? So at the beginning, we're going to have v connected components. right? So before we put in any edges, we have all these vertices, they're singletons. Okay? So we have V connected components. At the end, how many connected components do we have? We have one, right? Because it is a connected graph. Okay, so that's just one connecting component. Now, what happens in between at each iteration? We go from some number of connected components, I don't know, like, it's a nice letter here, A, okay? So let's say that we are, at some point, we have A connected components, and now we throw in an edge. Okay, what do we expect to happen? So we don't expect the connected components to go up, right? It either stays the same or it goes down. Why should it go down by 1?
First of all, it must go down. And then secondly, it must go down by 1 because you only add one edge. You cannot go down by more than 1.
No, I agree they cannot go down by more than 1, but why does it go down by at least 1?
Because, say, if you add another edge to an already connected component, you will create a cycle.
Great, okay, so it must go down by exactly 1. Why? Because if it didn't, like I'm connecting two things already in the same connected component, I will get a cycle, right? Because the two things that are already in the same connected component, by definition, they already have some path. That path is not this edge that I'm putting in because it's not there yet, right? When I put it, I'll create a cycle. But that's not okay because when I put in all the edges, there's supposed to be no cycles, right? So it goes down precisely by 1. Okay, so at the beginning we have V, at the end we have 1. Every time we do an action, it goes down by 1. That means that overall, we must have exactly V minus 1 edges. Okay? Okay, because we... Okay, is it clear? All right. So let's look at the reverse direction. Namely, if G is connected and it has V minus 1 edges, then it is a cyclic. So let's think about it like this. Suppose G did have a cycle. So we can think about it like this. So while G has a cycle, remove an edge from that cycle. Okay, so we want to prove that G actually has no cycles, but whatever. For now, let's just assume if we see a cycle, we remove any edge from it. Okay. Notice that this operation done over and over again, no matter how many cycles we see, will leave G connected, right? Because removing an edge from a cycle cannot disconnect a graph. Okay? Because you had two ways to go from the two things, right? If you remove one, at most one path goes away. So, so G remains connected. Okay, but or rather G, let me kind of give a name to it. So let me call it, we get G prime that is connected. And now it is a cyclic, because we've removed all the cycles. Right? So we just took G, and we start removing, every time I see a cycle, I just remove an edge. Obviously, I'm modifying a graph, so here's the end of that operation, at the end of all such operations. Now it is connected in a cyclic. But wait a second. We already know that a connected acyclic graph has exactly v minus 1 edges, right? So we know that G prime has v minus 1 edges, right? But how did we obtain G prime? It came from G, right? And G already had v minus 1 edges. So we couldn't have removed really any edge. But the only reason why we would have removed an edge is we had seen a cycle. Okay? So it means that G was acyclic. Okay? G is acyclic. In fact, G equals G prime. Okay? So, kind of, we proved both directions. Okay? We did leverage the proof of the forward direction in proving the backward direction, but we did have to say something. Okay, so this is just, be comfortable with this type of simple small arguments so they give you some familiarity with graphs and their properties. Cool. Another property of a graph that we're going to use is that if G is a tree, then for every distinct, you know what, I actually want to do it in a different word. So space. If G is a tree, then for every distinct two vertices u and v in the vertex sect of G, you have a unique path from u to v, and vice versa. Okay? So being a tree is equivalent to having a unique path between any two pairs of distinct vertices. All right? So let's look at this direction, or at least this direction. Can anybody argue why if G is a tree, then there's a unique path between U and V? Yeah.
Assume G is a tree, but there's two paths, and you have a cycle. But G can't have a cycle.
Okay, so on the one hand, if G is a tree, but there were two paths from U and V that are distinct, then we would find a cycle. What if there are zero paths? Then what goes wrong? It's not connected, okay? So, done, right? But you see, kind of like, it's important, now we're able to understand, because we understand the structure of trees, we're able to kind of see these things a bit more, right? So, now let's say that we have some graph, and all we know about it is that there is a unique path between two pairs of distinct vertices. Why should it be a tree? We're kind of saying the same things again, right? So first, well, the definition of a tree says it's connected and acyclic. Having a path between two pairs of vertices, that is connectedness. Okay, so that's definitely connected. Why would it be acyclic? Well, because if we had a cycle somewhere, we would be able to find two distinct paths between two vertices on that cycle. Okay? All right. So I do encourage you at home to kind of look at these statements and make sure you're comfortable with them. There's nothing tricky about them. It's just the notion of a tree you may have seen, like as a binary search trees or these like things with the root on top. Here it's kind of like a flat sort of type of tree with no distinguished root, right? You need to be able to understand it abstractly without thinking of children and sort of siblings. That's not quite the way to think about trees here. Okay. So now that we understand trees a bit better, let's start connecting what we've learned about them to MSTs. Okay? So now we're going to prove kind of the core cut property, and there we're going to prove something else about it for the algorithm. So essentially what we're going to prove is that at least our first choice here was safe. Okay? So we want to say that because 1 is like the cheapest, it's okay to pick it, meaning that we'll be able to grow it into an MST. Okay? And we'll see that later, intuition will say that we can recursively continue in this way, right? Pick the next cheapest that preserves, that doesn't create a cycle. So let's prove it. And the way you prove it is you have to reason about cuts. So first, let's define a cut of a graph. A cut in G is a sort of any pair of the form S and V minus S. Okay, that's exactly a cut. It says, here's a subset of vertices on the left, and here's the rest on the right. This is figurative, like they may not be on the left or on the right. Literally, we're just designating certain vertices as being on one side and the remaining ones on the other side. And here's the claim we're going to prove. That the cheapest edge in any cut is part of some MST. Okay, so the picture you should have in mind is something like this. So we write down a cut. It's really an arbitrary cut. Because we'll be considering kind of graphs that are connected, right? Because eventually we want a minimum spanning tree. There will be edges crossing this cut. This one, this one, this one, this one. All of these have weights. One of them, or some of them will have a minimum weight crossing this cut. Okay? Let's call it E. Okay? What this claim says is that it is possible somehow to grow this into an MST. Okay? So we're going to prove this, okay? Pick any cut, look at the cheapest edge crossing it, all right? That can be grown into some MST. Coming back to this example, we could have thought, look, is it safe to pick 1 as the first option and say, well, let's consider the cut of E and everything else? Okay? Now, these 3 edges cross it, right? 1 is the cheapest among them, so I know that this guy is in some MST. That claim doesn't still tell me how do I continue, but it does tell me that picking this one was okay. By the way, it also says that picking this one was okay, right? Because I could have picked this cut, right? And among 5, 4, and 2, this was cheapest. It would have been also a reasonable starting point, okay? But it still doesn't tell me how to continue. But let's start with that one, okay? Okay. So let's go to the proof. Right, so pick any MST. Okay? And we're going to assume that E is not in the MST. Otherwise, we're done. Okay? So we're going to derive some contradiction. So the MST must cross the cut somewhere, right? Why? Because the MST spans the whole graph, and the cut cuts it. So the MST must cross it. So here's a picture. We had our cut that we chose. We had a cheapest edge, but for now, it's off somewhere. Then we have our MST that we pick. It crosses somewhere. Let's call that place E prime. Right? By the way, the MST also reaches the endpoints somehow of E, right? Because E kind of lands onto vertices, and somehow the MST must also reach those places, right? But E at this moment is not part of the MST, but the MST crosses the cut at some edge E prime. All right. Can I get rid of this proof? Now, what we want to do is want to prove that E is part of some MST. Now, we have an MST that doesn't contain E. It's T. But at least we got something, okay? We can handle. Can anybody suggest how we may modify T into another MST, T prime, that does contain E? Yeah. The suggestion is to remove E prime and put in E. Sounds like a good suggestion. Let's go with it and see that it works. So we're going to consider T prime obtained from T by deleting E prime and adding E. All right? So we need to convince ourselves that T prime is an MST. Now, first and foremost, we should convince ourselves that T prime is at least a tree, right? Otherwise, it's got no chance to be a minimum spanning tree, right? So first, T prime is connected. Can anybody explain why T prime is connected? Yeah. Yeah, I think that's a reasonable answer. I think it works, but here's maybe a shorter answer. How do we go from T to T prime? We go to an intermediate graph, I don't know, T double prime. It's not a tree, but it has a cycle. So when we leave E prime and we add E, we have created a cycle, right? And remember that when I remove any edge from a cycle, I leave the graph connected, right? So when I remove E prime, that is part of a cycle, which cycle? This one, right? Here is whatever way you go from here to here, there must be some way. Whatever way you go from here to here, there must be some other way, right? That's a cycle, and if I remove E prime, I cannot disconnect the graph. Okay? So T prime is connected, okay? T prime also has V-1 edges. That's easier, right? I mean, I added one edge, I removed another one. I had started with V-1 edges, so this is what I get. Now, these two things tells us that T is a tree. T prime is a tree. Okay? What about the weight of T prime? Well, the weight of T prime is whatever weight we had before minus the weight, should be W, the weight of E prime, which we removed, plus the weight of E, right? But remember, what was the property of E? E was what? The cheapest across the cut. So that means that E, and moreover, E prime is crossing the cut. Okay, so the weight of E is less than or equal to the weight of E prime. So it means that this entire thing is at most the weight of T. So T prime is just as good, if not better, but T is optimal, so T prime cannot be strictly better. So we've proved that T prime is an MST also. Okay? Okay, so this is the cut property. Notice that again, this is again no relation to shortest paths, because potentially there used to be a good way maybe to go from here to here. Now we're considering some other MST where you go this other roundabout route, but that's okay. Okay, the total weight of the tree is too small. Okay, so the cut property as currently stated tells us that it's okay to get started by picking cheapest edge across some cut. But we don't know yet what happens when we've already chosen some edges, okay? And we want to continue, because we cannot just pick a next cut and pick the cheapest edge, because it could be that MST, the partial MST that we currently have, and the MST corresponding to the edge that crosses the new cut that we're considering are distinct, okay? So I need something a little bit more refined than this one. So what I'm going to do is I'm going to prove some sort of a more refined cut property, where we'll do basically a very similar argument, but the statement will be slightly more refined so that we have kind of state about past edges that were chosen well. Okay? We're going to inductively assume that if I have some edges that are part of MST, and I pick something, then I can continue extending to some other MST, possibly. Okay? Any questions about this proof or the statement? Again, once you're familiar with trees, this proof shouldn't be complicated. Right? That's why we kind of spent 15 minutes on trees first. Okay, let me do it here. So, okay, the claim is going to look rather analogous, but we're going to have some edges to start from, okay? So suppose that I have some edges that are part of some MST. T. Okay? That's kind of my inductive hypothesis. And also, and these edges do not cross some cut. Okay? So inductively we have some edges, and now I'm considering a cut that is a cut that is not crossed by X. Then, if E is the cheapest edge across the cut, then what should my conclusion be? What do I want to be true? So I've written almost all the claim. What do I want to be true for me to make progress? So I've made progress in the past. I have X things I have things in X that are part of some MST. Now I look at some cut not crossed by X, and I pick the cheapest edge. Now, probably I want to make progress, and I want to take this edge and put it in X, right? So I will say then X union E. What? What would I like to say? It may not itself be an MST, but we want it to be part of an MST, right? But maybe it's a different one, right? Maybe it's not T, okay? So in some MST T prime, okay? this is a kind of strictly stronger statement than the previous one. The previous one is just this statement, where this is the empty set. Okay? So we'll just do another proof, which is basically pretty much the same proof. But we'll just do it again so you get familiar, and also because we need this. Okay? I didn't want to start with this one that is more complicated. Okay? So the picture for this statement, let's see it. So what you have is your cut. Okay? And you have kind of your x edges are on the two sides, but they're not crossing. But what you do have is the cheapest edge that crosses, that's E. And we're saying that because it's the cheapest one, there is a way to kind of extend this to an MST. Or let me put the also part. The other hypothesis said that there was an MST of some sort that was connecting these, possibly crossing somewhere else. And what we're saying is that it's okay. You can, because you have this, there is a way to kind of extend and cover all these things, possibly with a totally different MST. But you don't care because you just want to be able to continue the inductive hypothesis. Okay? So that's just, so maybe the picture is not super beautiful, but I wanted to visually show that X doesn't cross the cut. So let's prove that this claim. And it will be really like an analogous proof. All right, so once again, we're going to assume that E is not in T, else we're done. Okay, because if the cheapest edge that I pick across the cut, it's already in MST T that I had, well, then I'm done, right? So let's see what happens if it's not the case. So the MST must cross somewhere, say at E prime, which is different than E, right? So MST goes everywhere, okay? It contains X, of course, but when it crosses the cut, it picks an edge E prime that is neither E. In fact, it's also not in X, okay? Now we're going to kind of want to make progress. We're going to construct T prime obtained, again, by deleting E prime and adding E. Okay? And the reasoning is the same. So let's make sure we're comfortable with it. Do it one more time. This cut property is going to show up many times in homeworks and probably exams, so make sure you understand it. So various things. So T prime contains X and E. Okay, because notice that the way we went from T to T prime is we knocked out something that was not in X. Okay? It is not in X. So I kept all of X inside and I'm adding E. Okay, so now I know that T prime does contain X and E, which is what I eventually want, right? Moreover, as before, T prime is connected and has V-1 edges. Namely, T is a tree. Right? Why is it connected? Because I created a cycle by adding E prime, then I broke the cycle by adding E, and then I broke the cycle by removing E prime, so it remains connected. I started with V-1 edges, I added one, removed one, I end up with V-1 edges, so it's a tree. And by a similar argument as before, the weight of t prime is at most the weight of t, simply because the weight of E is at most the weight of E prime. Okay? So this says that that concludes the proof. Okay? Is it clear? All right. So now it should give us an idea of, coming back to here, what we should do, right? So let's say when we pick 1, now that becomes our x, right? And we're going to continue and make the next choice. So really, this claim says that it suffices to pick any cut that is not crossed by 1, okay? And then pick the cheapest edge crossing it. And we throw it in the bag, and we keep repeating this, okay? And at the end, we're done, okay? So, but let's try to turn this into like something more precise. It will actually help to pick edges in order of their weight. It's not the only order that you can pick. There's other algorithms that pick slightly different orders, but we'll look at this particular one. Yeah, so let's do that. Let me do it up here. Right, so now we're going to look at, finally, an algorithm for MST. This is called Kruskal's algorithm, after a person that invented it. So the inputs are G and W. Okay? So what it's going to do, it's going to sort the edges by weight. In increasing order. So we start with the cheapest edge, and then kind of for each E in this order, you're going to reason as follows. If adding E creates a cycle, skip it, else add to the tree T, and at the end you just output whatever tree you have. Okay? So now what I want to do is I want to show more precisely how to use this claim here, okay, to prove that this algorithm is correct, okay? And then we're going to later talk about briefly how to run this algorithm, because notice this algorithm, this step here looks pretty simple, just sort the edges by weight. But this part here is like less clear, right? Kind of in the middle of some loop, now you want to check if there's a cycle. Again, algorithms don't have eyes, they're not just looking at the graph for cycles, they have to look for it somehow. But let's put on hold for a moment how we're going to look efficiently for a cycle here. Okay? Let's just first convince ourselves that this algorithm as written solves the problem. Okay? I also want to say that this is a greedy algorithm. Why? Because, look, it sorts the edges. Okay, that's like a one pass. After they're sorted, it looks at each edge, it either picks it or not. It never comes back on its choice. It doesn't ever pick an edge that was added to the tree and remove it. So this is a greedy algorithm. Okay? Like technically maybe it's like half greedy because sorting is a bit of a global operation, but I think it still morally falls under the the umbrella of greedy algorithm. Okay. So why is the algorithm correct? So so anybody want to try to explain it? So the first choice the algorithm makes is the cheapest edge, period, right? So why is that a reasonable choice? Who tells us that's a good choice? Yeah, that one says it's a good choice, right? So now, after the first iteration, we have x equals set of cheapest edge, right? And we know it's part of some MST, right? All right, so the next choice is, whatever next edge creates a cycle. Maybe the next edge is, something that connects back the same two vertices in some other way, and so you skip that, right? So you go to the next cheapest one that doesn't create a cycle. So if it doesn't create a cycle, then how can we apply this claim to argue that we make progress? Sorry? Sorry, I didn't understand. New vertices. I'm sorry, I didn't understand. If you speak louder and slower.
A new vertex was visited.
I am so sorry. I didn't understand it for the nth time. A new vertex, that?
It was visited.
Oh, was visited. A new vertex was visited. Wait, hold on. But syntactically, what I need to find is a cut, right? In order to apply the statement, it's not about necessarily vertices, it's about cuts, right? If I want to apply this statement, I need to say there is a cut somewhere, right? So how do I need to define this cut? What should my cut be? So while you guys think, let me just write the first step here, kind of the base case. So that's the base case that we just discussed. An inductive step. Let me just spell it out slightly more clearly. The inductive step is that we're going to assume inductively that current X is in some MST. Okay, so now this is where we are at now, and that's what we want to discuss, right? So we've chosen some edges. Now we pick the next one that doesn't create a cycle. Where is the cut? Like, we need to somehow relate this not a cycle or doesn't create a cycle to cuts. Okay, because that's the language in which we understand the next edge. Okay? So how do we phrase that? Yeah?
If we make S to be the set of vertices that T touches, then we're finding the cheapest that touches A.
Where is T? So, okay, yeah, no, there is T here. I don't want to confuse it with the other T, the T that is actually full. So this T is kind of partial. Let's call it X for a moment. Okay? So you want to define the set of edges from X? All vertices that S. Wait, we need to define S, right?
I mean the X, the T.
I probably should maybe write I'm going to stop using t here. I'm going to use x, okay? And that is our working variable, okay? So x is given to us. It is whatever we have currently in Kruskal, okay? So what I need to define is s. How do I define s?
Yeah, what I'm saying is, can we define S as all the vertices that X touches?
Maybe, let's try that. Yeah, no, and also, yes, we should be aware of that x is a set of edges, and s is a set of vertices. These are different types of objects, so that's at least one conversion we should do. So let's talk about that option. Yeah, so the question is, we can repeat the inductive step. So we haven't finished it. This is just a start. And saying, assume inductively that the current x is in some MST. Okay? This is true in the base case. Then we're going to assume it inductively. We just need to make sure we can make progress. So Kruskal picks some E that does not create a cycle. What does it mean? Well, we have chosen, a set of edges x that define a part of the graph, right? Are these edges in the same connected component? So we have x, and the next state of the algorithm is x union E. Right? Question. If I look at the subgraph defined by x, are they all in the same connected component? No, right? In fact, if anything, x will look like things that look like that, right? Because if they had been the same connected component, all of them, and I would add an edge, I would get a cycle. But that cannot be, because the algorithm adds an edge only when there are no cycles. So we should at least have two connected components in X, right? So maybe there is more, but that's one, that's the other. Again, maybe there is more subcomponents, but they can find at least two. All right? I can, because E does not create a cycle. All right, but then that's the cut. I can just, pick arbitrarily edges in one connected component and all others. Okay? Then I convert from edges to vertices, and I get my set S. Right? And I can pick the cut, a cut where E is crossing. Right? Right? And because E is the cheapest edge so far, it must be also the cheapest in the cut. Okay? Because if I have already chosen some other edges, they will already be in X. Okay? And if I skip them, it's because they create a cycle. So it means that they are between things that are within the same connected components. Okay? There are things to say here. You notice, like the conversion between this claim and why this works, somewhat non-trivial. Okay, you have to keep track of these connected components. Let me try to say it again. We're picking edges in order. Okay, it's important. Okay, because this picking them in order lets us link back to the claim. How is it important? Because we are somewhere in X, and we're inductively assuming that it's part of some MST. Sure, that's fine. Now we need to get our handle on some cut where the choice of the algorithm coincides with picking the cheapest edge in that cut. Okay? Now, because E doesn't add a cycle, I know that X is at least two connected components. All right? So, arbitrarily, put not arbitrarily, put a cut, okay, that E passes. It must pass in some cut, okay? So here it is. And, throw X in either side as it happens through this cut, okay? But we're not done yet, right? We need to also argue that E, chosen by the algorithm, is also the cheapest across this cut, okay? So, well, how could it be? Well, the only cheaper things are the ones that came before. So who came before me as an edge in the algorithm? Either things that were picked already, okay? But if they're picked already, they're in X already, okay? Or things that created cycles. Those cheaper edges must have been already part of previous connected components because they did create cycles. That's why I skipped them, okay? So they cannot be among those that cross right now because crossing means connecting connected components, okay? All right. So that was said twice, and maybe that's enough for now. Make sure that you kind of go over it at home, okay? I think that both the simple cut property and the extended cut property are pretty straightforward, but going from the algorithm Kruskal and its correctness to connect it to the extended cut property requires some care, okay? I didn't write all the text out, otherwise it take forever, okay? I want to talk a little bit about the running time of the algorithm, okay? Yeah.
Using the same argument, instead of picking the cheapest edge every time, wouldn't it be easier to start at a vertex and grow the tree with the cheapest one available, so that S is always what S is. So things that get touched.
There are other orders, I think 2 other orders to pick edges to create MST, and I think they're also described in the book. We're not going to go over them in class. They may appear in some homework, I'm not sure. But yeah, there's other orders one can pick. This is just one that helps you prove things. I haven't thought, I don't remember right now whether the other one is strictly simpler, roughly the same complexity to argue it. I want to briefly talk about the running time of the algorithm because it's not really fully spelled out kind of what happens computationally, okay? So let's do a first idea, sort of to implement it. So the cost of one, well, for this part, we can all agree we just sort edges as we sort anything. So that part is easy. So the cost of the second step, the loop. So we have E iterations, one per edge. And for each edge, we have to check whether there is a cycle or not. We've seen how to detect cycles. What should we run? We do DFS, right? A cycle is identified by a back edge, right? So the second step of the algorithm, we can definitely bound it by, so this is the outer iteration, and then the cost of DFS. The cost of DFS, remember, is size of V plus E, right? First, I'm going to say this is not terrible. It is polynomial time, which is non-trivial. Yeah, it's kind of annoying, right? You have this quadratic blow-up, okay? And really, if you think about it, it's a bit wasteful to run DFS every time, right? Because you run DFS one iteration to figure out whether there is a cycle or not. And you go through the graph and you kind of annotate all these things. The next time you run DFS, the previous graph has barely changed. You added one thing, one edge, right? So somehow, it's wasteful to rediscover everything, okay? So it turns out that if we are a little bit more precise, there is a kind of a fine-grained data structure that suffices to implement this algorithm. We're going to talk about the API right now, okay? This is called a union-find data structure. And its implementation is actually the subject of an entire lecture, which is the next one, not this Thursday, next Tuesday. Okay? But I want to show in the algorithm how the API of the data structure will help us. All right, so this is kind of, I'll just conclude here and say, okay, but not great. But anyway, when you get a running time that is okay but not great, doesn't necessarily mean you can make it great, right? So here, there is a concrete observation that suggests that you're leaving money on the table. That is that you're running DFS at every iteration, and each time the graph is barely changed, right? So it really doesn't feel like you should be doing all this computation over and over again, right? So the idea for faster Kruskal is that we're going to maintain the connected components along the way. So the picture you should have in mind is that, look, at the beginning of the algorithm, we have no edges chosen. So kind of all edges, sorry, all vertices are their own connected component. Right? And now we've sorted the edges already, and now we pick the cheapest one. Now, when we pick the cheapest one, right now, nothing interesting is nothing interesting is already there, so we just kind of throw it in. What is going to happen is that these connected components merge. Right? Now, whatever this vertex was, now they are both should be labeled by the same connected component. Right? Now, when I pick the next edge on my list, and I'm wondering, will it create a cycle? What question should I be asking about the connected components? Yeah? Great. So I just basically want to look up two pieces of information. The connected components of the two vertices that participate in the edge. If they are distinct, it's safe to add the edge. If they're the same, I skip the edge. Okay? So, for example, here, if I continue and the next cheapest one is, say, this one, and I look up the connected components of these two, they will be distinct. Boom, I add it. Now the data structure will update the connected components to be the same. Okay? Maybe I add this one next. This becomes one big connected component. All of them get updated to be labeled by the same connected component. But if, for example, after I am considering this edge, whether to add it or not, okay? Because this is a connected component, adding it will create a cycle. Okay? So really what I need is a data structure to keep track of connected components. All right? So I want to be able to merge sets of vertices that previously had distinct connected components, and I want to update them to have the same connected component. Okay? So slightly more precisely at the beginning, we're going to say for every v in the vertex set, we're going to so-called make set of v. This creates the initial singleton sets. Okay, so I am associating to every v a unique set ID, basically. Okay, its own connected component. Then at each iteration, we're going to find u and find v. This will look up the connected components of u and v. Okay? That is over here. And if they're the same, we're going to skip e. And if different, we're going to call the operation union UV, which says, look up the set of things that have the same value as U, its whole connected component, and its whole connected component V, and you merge them all. Okay? So the operations of data structure that are kind of relevant is union and find. Yeah, of course, there's also the initialization there. But so that's why this data structure is called union find. Okay? So let's count how many such operations are there. Okay? So we have size of V make sets. Right? How many finds do we have? Yeah, roughly 2e, right? Because we are in the undirected case and we kind of consider yeah, not just E. What is it called? Find. And then we have how many union? V minus 1. Okay? Because we're only going to add V minus 1 edges. Okay? Now you will see the next at the next lecture that all of these can at most cost each of them cost at most log V. Okay? So that overall the running time of Kruskal is E log V. By the way, where did the log E go from up there for sorting? I claim that this is actually running time of the whole algorithm, assuming this is the case. Why don't I have to write E log E here? Yeah, yeah, E is at most V squared, okay? So, log of E is the same as log of V, okay? The power there doesn't matter, it just becomes a constant in front, okay? So, using a data structure that you will see next time, this is the running time of Kruskal. Notice this is better than this one because here you have this term of E squared. Okay? Now, there was one clarification from last time that there was a question that I wanted to kind of briefly address. So when we discussed scheduling, there was this case where we had the optimal S and the greedy G, and we're assuming that they differ somewhere, okay? And there was a question, what if the schedule of S is, 3 classes, and G is 4 classes, and they differ nowhere. This is equal, that's equal, that's equal, okay? So what I failed to kind of describe clearly in lecture is that this can never happen, because if you have a greedy solution, you have a greedy, so we wanted to schedule the maximum, sorry, this way. What I failed to say in class is that if you have a greedy solution that is suboptimal because it chose these 3 and it didn't choose anything else, but the optimal one picked these very same 3 plus this one, well, the greedy algorithm would have also picked it because the greedy algorithm was going to pick stuff as long as it was possible, right? It would have also picked this one. So this is kind of like a subcase, a simple subcase of the proof that tells you that you can indeed assume that S and G differ somewhere. Okay? All right, just a small clarification from last time. There is going to be no lecture on Thursday. There is a midterm, so go to that one. And good luck.